Hello all, I am Pedro Valois, and this is the presentation for the WASCV 2024 paper titled Occlusion Sensitivity Analysis with Augmentation Subspace Perturbation in Deep Feature Space. This presentation starts by motivating what is interpretability and show an example. Then, we will explain our new metric, technique, and compare results accordingly. Interpretability. In simple terms, the goal of interpretability techniques is to understand machine learning models. That means to understand why it failed in a certain situation, but also to understand why it didn't fail on other circumstances. In the end, we wish to make the model more predictable and thus less prone to malfunctions or hallucinations. From this point of view, the model is a black box function which just receives an input and provides an output without we initially knowing any of its inner workings. In this field, there are multiple different interpreters, but our focus will be on perturbation-based ones. A common example of a perturbation-based interpreter is occlusion, also known as Occlusion Sensitivity Analysis, OSA. In this method, an image is input and multiple random noise masked versions are constructed. After selecting a label, we can use the variation of the model probability output as a proxy for the occluded region importance, putting all together, and we can get an explanation heat map, which locates the most probable cause of the model prediction. This technique has the advantage of being completely architecture agnostic and having a simple to understand heat map. However, sometimes need to build one explanation for each label to generally understand the model, which is not always desired. Also, it is vulnerable to a distribution shift, as not all models will be ready to handle occluded inputs and thus behave poorly regardless of occluding an important region or not. More formally, we can use causal theory to define an equation for explanations. This equation communicates that an explanation of a model F given an input X is the minimal subset of pixels of the input which keeps the same original output. But simply, if we have an image which the original output for the model is sheep, this could be a valid explanation. However, in this case, despite the smaller size, the output now changed, so it is not a valid explanation anymore. And neither this one. With that in mind, we propose our new interpretability metric. The minimal size metric measures the ratio of the number of pixels in the explanation over the original number of pixels. For example, let's say I have three different interpreters and their respective explanations E1, E2, and E3. We can measure their respective ratios easily, and their best interpreter would be the one with the minimal size among the three. Finally, we introduce OSA-DAS, our novel interpretability framework. Our proposal hinges on a simple premise. If data augmentations are so prevalent in model training, they can be equally instrumental in enhancing interpretability. First, we feed both the original images and their augmented variants to the DNN model. Then, we get a set of deep feature vectors, those that are before the classification hat, and apply principal component analysis to build the basis of a subspace which serve as our reference in the latent space. Now, we apply an occlusion to the same input image, augment the occluded version, and feed all variations to the DNN model. Then we apply PCA again to build a new subspace, now representing the influence of this specific occlusion on a range of inputs. Finally, by repeating this process to multiple occlusions, we use the subspace similarities to compute the occlusion importance and produce the final explanation heat map. Our technique not only keeps the advantages of OSA, of being architecture agnostic and easy to understand, but now we have a class agnostic and distribution shifts resistant method, as we use augmentations the model already saw during training. On the other hand, it is now more time and memory expensive than the original OSA. To balance out this difficulty, we can use the gradient of the model with respect to the input to propose better anchor regions. This is a better approach than using simple random masking. This improves the convergence rate of our technique, as we can use less mask than needed before. We try our method on ImageNet 1000 with ResNet 50, Visual Transformer B, and Swing Transformers V2. Our qualitative results show that our explanations are more concise and also resistant to model misclassifications, surpassing regular OSA and other techniques. Furthermore, the quantitative results also confirm the overall performance of our technique among multiple metrics, including minimal size. Lastly, we try to understand how the technique behaves on different configurations. We show that the augmentations are necessary to the technique performance. Also, the technique is resistant to very strong augmentations, keeping the same performance up to a certain point, from which it collapses. Beyond that, we also verified the need of subspace representation to our technique success, where the number of canonical angles represent the amount of shared information needed to be computed between subspaces. Thank you for watching this presentation. Please refer to the main article and supplementary material for details.